Guys, let's just let other people join the class. How you guys doing today?
Not bad. How about you?
Good, thank you. So hopefully this is not a surprise. Just a reminder that we have a test tomorrow, chapter 3, chapter 5, and 4.5 and 4.6. And the will open up tomorrow at the beginning of our class time, so we will not have class. So you guys will have a 24-hour window. So starting tomorrow at 1:35 until Friday at 1:35. Okay, so keep that in mind for your exam. And we won't have class because you guys can take the exam during the class period. I am not technically allowed to double dip. Sure there's been any change in what's on the exam. So just like I just said, chapter 3, chapter 5, and chapter 4.5 and 4.6. So the chapters that we covered in chapter 3, which is chapter 1, chapter 3, 3.3, 3.5, right, and 3.9. Okay, so all the stuff that we homework assignments for. Okay, so today is your day to ask questions. I am happy to ask questions. I kind of want to encourage you. I know that our homework for 3.9 is due tomorrow, but that is only a small fraction of the exam. So please ask questions about a lot of other things too, if you have questions. Homework solutions will be uploaded tonight. And that'll be at the top of our modules page. I have to give time for, make sure, like I said before, to make sure that I'm not interfering with other classes. Plus also it's good for you guys to work through the homework too and ask. 3.9, number 20. Okay, I'll do 3.9 and then I'll do exam 2020. Give me just a second. I'm just gonna go in order that I see them. Let me just give me a second to get it out here. We can also go over the quizzes. By the way, the quiz solutions I uploaded to like the modules page of where the quiz was posted originally. So if you're looking for quiz solutions, they're like, if we had a quiz on week 6, the quiz solution is listed right below on the module where the quiz was posted. What was it? 3.9. Number 25. Okay, so 25 is like a, we've got this work problem and we have a bucket. Let's see, let's start writing it out. So we've got a bucket that's being lifted and the bucket's leaking, right? So let's say we've got our bucket. It starts off as with 80 pounds of sand, but it's leaking at a rate of 0.5 pounds of sand per second. Okay, and we're gonna take this bucket and we're gonna lift it up 60 feet. So we're gonna go from 0 feet to 60 feet. And the force that we have is a gravity force, right? And we're lifting it at a constant velocity of 4 feet per second. Okay, so all these things we're going to need in order to figure out what the, I didn't post the solutions for the spring 2020 yet. I actually just found them today. So if I remember, I will scan them in and post it, but I'll answer whatever questions you have on those. Let me just finish this one first. All right. So now what we have is a force due to gravity, right? So initially, right, we're dealing with 80 pounds. So it's pounds, which is a weight, right? Which means that gravity is already included in that. So I don't have to multiply by gravity. This is in feet. So I wouldn't be multiplying in 32 feet per second squared. It's already there because it's in pounds. But we're losing weight, right? As we lift this up, there's sand leaking out. So we have to take that into account. So we've got 80 minus, this is 0.5 pounds per second. So if I go 0.5 times the seconds, that'll tell me as of this moment, as of this point in time, how many pounds have we lost, right? So 80 minus that is going to tell us what's our current weight, right? So this is our current weight. So this is our force. But now, I'm moving this up. This is like in my y direction, right? I'm going from 0, y equals 0 to y equals 60. So I need to be thinking about things in terms of, I'm going to integrate 0 to 60 with respect to y, dy, right? Because y is my differential there. So I need to convert this t into y. So I also need to factor in my velocity, right? Because how fast am I going is going to influence how much sand leaks out too. So if we've got our velocity equals distance over time, which our distance is a vertical distance. I'm going to call it y over time. And this is equal to 4 feet per second, right? So now if I solve this in terms of time, I'm going to cross multiply and divide. I'm going to get time equals y divided by 4. That's a 4. Okay, so now I've got, you know, time in terms of y, which is good because I'm going to take this time and I'm going to plug it in for that right there. Okay, so now I'm going to write my force equals 80 minus 0.5 times y over 4. So this is 1/2 times 1/4, 80 minus y over 8. Okay, so I'm going to put this in here, 80 minus y over 8 dy. And then it's just simple integration, right? So make sure, I'm not going to do out the rest, but antiderivative, you're going to want to show. And then you're going to get as an answer 4575 foot-pounds. Okay, and then let me get out my exam. Give me a second. 2020. Okay, and then you want to look at number 11. Okay, arc length. By the way, question number 12 on that exam that deals with a mass of a plate. I'm sorry, that's no, it's a volume of revolution. Solar revolution. Where do we have the mass of a plate? Do we have that on here? So if we don't have that on here. If we've got like mass or density functions on some of these old exams, we didn't get to that. I think that was chapter 3.7, so you can ignore those questions. All right, so this is exam from spring 20, and we're going to do question, you said number 11. Okay, question number 11. So we've got find the arc length, right? So I'm going to go of my function equals x squared plus 2 to the 3/2 all over 3, and we're going to go from 0 to 1. Okay, so remember our arc length, right? We've got our bounds a to b, 1 plus our derivative squared, square rooted dx. I can do this dx dy squared and then make this in terms of dy, but we already got this function in terms of x, so we're good. So I have to take the derivative. Okay, so remember, this is like a 1/3, right? So I'm going to go my exponent, 3/2 times 1/3. That's from the 1/3 here. X squared plus 2. I have to subtract 1/2, and then I've got a chain rule, 2x. Okay, so this is going to look like, let's see, I'll go 2, 6. This is 6x times x squared plus 2 to the 1/2 all over 6, which just becomes x. Let's see, x squared plus 2 to the 1/2. Okay, so this is our derivative. Okay, that gets plugged into here. So then our arc length equals, and we're told to go from 0 to 1. I'm going to go 1 plus my derivative x squared plus 2 to the 1/2 squared square rooted dx. So now it's just algebra, right? So this is going to be 1 plus x squared times x squared plus 2, which is x to the 4th plus 2x squared plus 1, which means that we're dealing with, this is actually, this is a perfect square trinomial. So this is going to look like x squared plus 1 squared, which is just simply x squared plus 1 dx, which is now just power rule, which then becomes 4/3. Okay. Let's see. Question number 11, question number 2, AB. Okay. Use of convergence interval. Okay, great. Yep. You guys will have this one here before I yeah, Kartiki, give me a second to answer these and we'll talk about the calculator, okay? Calculator is just meant to help you. We used to actually not allow calculators in this class and we've kind of eased up over the years. So everything that you do can be done without a calculator, but you have to show the algebra. It's not enough to do a graph and then say, here's the point of intersections of the graph, unless we're talking about like, we're looking for, you know, where does the function cross the x-axis in? It's like a cubic or a fourth root or something like that, and you need to use that to help you find it. But well, let's talk about that in just a minute. So this is the spring 20 question number 2. And so this one says, given the following power series, k equals 1 to infinity, x minus 1 to the k, k to the k, k plus 1 to the k. We want to find the radius of convergence in the interval of convergence. Okay, so our radius, this is part A. To find the radius, we're going to need to do the ratio test. So I'm going to go limit as k goes to infinity. So this is going to be x minus 1 to the k plus 1 all over k plus 1 to the k plus 1 all over k plus 1 plus 1, right? I'm substituting in for k to the k plus 1 all over our original absolute value. So now I have to multiply by the reciprocal. Okay. Okay, and I'm going to group things together just so we can see. Limit. So I'm going to go x minus 1 to the k plus 1 all over x minus 1 to the k times k plus 1 to the k plus 1 all over k to the k. And then I'm going to go, actually, I think I want to put this one, and I can go, what do you think about this? K plus 1 all over k to the k, and then I've got k plus 1 all over k plus 2 to the k plus 1. There. All right, so how do we need to think about this one? I think these two, yeah, I can group these together. So let's clean up this first. So the limit, k goes to infinity. So this is going to be x minus 1, right? Because these cancel out with the k's. And then I've got k plus 1 to the k times k plus 1 all over, no, I'm sorry, I'm going to leave it like this. So k plus 1 to the k plus 1, and then this over this. So it doesn't really matter. I've got, did I group this correctly? All over k to the, yeah, okay, I see it. I'm going to do this one. I think I have an extra hanging out here. Give me a sec to regroup. Yeah. K plus 1. Did I goof? Give me just a second. K plus 2, the k plus 1 there, and then I've got k the k over here. So then I multiply this all over that. Okay. All right. Well, let's just keep going. Okay. So now what happens is I have these things go to 1, right? And then this one here, why do I have k to the k? I think I've got, I think I'm missing something. Did I do something wrong? Let me just check for a minute, because k plus 1, k plus 2 to the k plus 1 all over k x there. This. So this one goes with there. This one goes here, and this one goes here. Yeah, I think we're good. And then these basically, we're talking about this one. They all basically cancel out to go to 1. I'm left with k plus 1 to the k plus 2 and k to the k. Why do I have, I think I had these switched here, and this one should be k plus 1. Oh yeah, that's why this is here. Okay, so I switched these. I got that wrong. Sorry. K plus 1, and then this one's going to be, okay, let me just rewrite this again. So I double dipped. I wrote it too many times. Too many. numbers. X minus 1, k plus 1. I'm just going to rewrite what I had because I couldn't figure out why I did it wrong, but I didn't. I just was writing it funny. K plus 1 all over k plus 2 to the k plus 1 times, this is going to be k plus 1 to the k all over k to the k. Good. Okay, now we have them all grouped. So this one cancels with this one. I'm just left with x minus 1. This one here, I've got k plus 1, k plus 2. These go to 1. K to the k, k to the k, these go to 1. So we're basically dealing with this is less than 1 to converge. Okay. So to converge, which means that my center is equal to 1 and my radius is equal to 1. Okay, which means that my interval is equal center minus radius, center plus radius. So I'm looking at 0 to 2. So now I have to do an endpoint check. Okay, this is part A, which says the radius of convergence, and then part B says interval. So we're going to do an endpoint check for my x values, right? So I've got 0 to 2, so I'm going to say x equals 0. I'm going to go back to my original series and plug in 0 for x. So I'm going to go, let's see, 0 minus 1 to the k, k to the k, k plus 1 to the k, right? I'm just doing it for x now. I'm going to check to see what happens. All right, so this is going to look like, this is minus 1 to the k times k to the k all over k plus 1 to the k. Okay, so this is an alternating series. I'm going to go the first check. K goes to 0, k to the k, k plus 1 to the k. This is equal to 1, which doesn't equal to 0, which satisfies our nth term test divergence, which means that it diverges at x equals 0. So 0 is not included. Now I'm going to do 2. X equals 2. 2 minus 1 to the k, k to the k, k plus 1 to the k. So this gives me just 1 to the k, k to the k, k plus 1 to the k. I've got k to the k, so I'm going to do the root test, right? Because I've got it to the kth power. So if I go the limit as k goes to infinity, kth root, k to the k, k plus 1 to the k. This is going to give me k over k plus 1, which is equal to 1, okay, which is inconclusive, which means I need to do the nth term test. Sorry, you can see that nth term test for divergence. Then basically I'm looking at the limit as k goes to infinity. Okay, this thing does not equal to 0. Okay, it's going to, at best, it's going to be equal to 1. K to the k over k to the k goes to 1. So it diverges also, which means that 2 is not included. So 0 to 2, not including the boundaries, is our interval. So Kartiki, when you ask about the calculator, are you asking about finding intersections using graphs? I think, so if you're thinking about like the quiz that we just took with the revolutions around, in this case, we did around a horizontal axis, we had to find the intersection of the two functions. You need to show the algebra on that. You can confirm it with your calculator, but you need to show some kind of algebra. If it's like we've got some kind of function and it's like we're doing like the displacement or total distance traveled, and we need to find out where does, you know, our graph go through the x-axis so that we can find that point, and say it's not quadratic, right? And we have to be able to factor it or find those values. You can use your calculator for that. 3.9. Yeah, I think, thank you guys. Let's see, 3.9 over 23. Looks like you guys were trying to help me out with the ratio test. Let's see, let me get out my homework. I think 23 is pretty straightforward. So 3.9, homework 3.9, number 23. So 23 says we have a mass that's 150 kilograms, which means we go to find the force, we have to factor in gravity. And then we're told that the delta distance is 3 meters per floor. And we're going from the 12th to 22nd floor, which is 10 floors. 10 floors, but then 10 floors times 3 meters per floor is going to give us 30 meters, right? So that's our distance that we're going. So our work, 0 to 30, we've got our force times dx, right, which is 150 times our gravity. Now we're in meters and kilograms, which means we have to do 9.8 meters per second squared times dx, or dh, you know, I guess because we're going up in height. So 0 to 30, this is just 1470h, 0 to 30, which I got 44,100 joules. I'm not seeing any other questions here, so let me kind of direct you. Let's talk about, I wanted to talk about this quiz that we took recently. I posted all these solutions in amongst where we had the quizzes posted, but the quiz for 5.3, 5.4, 4.5, 4.6, this one, the absolute convergence, if we wanted to do this one here. So whenever you're asked for absolute convergence, you also, if it converges absolutely, that's good. But you also need to find out if it's going to converge conditionally. Sometimes you won't be able to tell, like this one here is going to diverge when we take the absolute value, but it'll converge when we don't. So this is our quiz. So I've got the series k equals 2 to infinity, and I'm going to go -1 to the k ln of k. And we're asked if it converges absolutely. So there are multiple parts to this. I think if we do the ratio test on this one here, which will show absolute convergence, it's going to be inconclusive. So be careful. If you see this -1 to the k, that's an alternating series. So do the alternating series test first. So I'm going to go limit as k goes to infinity, 1 over k ln of k goes to 0. My second criteria is 1 over k plus 1 ln k plus 1 is less than 1 over k ln of k. So these are, remember, like I said, it's not enough just to say what kind of series test and what the conclusion is. You have to show how your series actually, you know, converges or diverges. In this case, right, it satisfies both criteria on the alternating series test to converge. Converges by the alternating series test. So now we have to check for absolute convergence. So I need to take the absolute value of my series. So what I'm going to do is I'm going to get k equals 2. This is going to be 1 over k ln of k. Okay. So I think I did this one. I think I tried it with the ratio test and it came out inconclusive. So, but when I see this, I've got ln of k. Ln of k is like a function, right? The derivative of the natural log is 1 over k. So this kind of makes me think it's like a function, which means I can do the integral test. Okay, so if I do the integral test on it, let's go ahead, which means I'm going to convert this. I'm going to go 2 to infinity. So let's just do a quick check. So we're in quadrant 1, 2 to infinity, right? It's a decreasing function and it's positive. Okay, so we're good. So it satisfies all the things I need in order to do the integral test. X dx. All right, so I'm looking at u substitution. So my u is going to be equal to the natural log. My du is 1 over x dx. All right, so I can plug this in. So I'm going to go, oh, and this is also, I need to convert this to a limit because it's an improper. So then I'm going to get 1 over u du, because I've got 1 over x dx already. So this is going to become the natural log of u, but I'm going to substitute back. Okay, so I'm going to get the limit as b goes to infinity of my natural log of the absolute value of the natural log of x. And I'm going to evaluate that from 2 to b. Limit as b goes to infinity, natural log of the natural log of b minus natural log of the natural log of 2. Okay. So natural log of infinity is infinity is infinity. So this thing diverges. My limit, let's say my limit does not exist. So the integral diverges, right? Because it's an improper integral. Since the integral diverges, that means our series diverges, which means that therefore our original series converges conditionally. It's conditional on it being an alternating series. If it's not alternating, it's not going to converge. So it's conditional on it being alternating. If it converged here using my integral test as well as with my alternating series test, it would converge absolutely. And like I said, I think one of my students in the 9 o'clock class asked about this being like, can I just do the ratio test to see if it'll work? But the ratio test on this one comes up inconclusive. You guys have this page here. I think it's week 6 is where it got posted originally, the blank page. It's under lecture examples. It's a blank page. You can fill this out or make one like it on your notebook paper. Then you'll have like a list. I think there's like 9 or 10 different series types that you'll want to fill in. It's going to be very helpful. Let's see, what were some other ones that I saw that I thought were good? Spring 2018, number 3, sure thing. Okay, yeah. Alrighty. So this is spring 2018, number 3. All right, so this one says, this is like the whole page that says, do these series converge or diverge? So we're looking at the sum n equals 2 to infinity, n over natural log of n to the nth power. I've got something raised to the nth power. Remember our whole checklist of how do we figure out what to do? So it's not an alternating series. It's not a p series. It's not something like geometric. I can't do like any of the special tests on it, but maybe, you know, it looks like if I tried to integrate it, I would be upset, right? So maybe I'm thinking, you know, I can do, it's got something to the nth power, so probably root test would work. But I'm kind of going through that checklist in my mind about what might work. So my root test says the limit as n goes to infinity, the nth root of n over a natural log of n to the nth power. Okay, which is going to give us, we want this, I'll put this less than 1 to converge. I'll put the question mark, is it less than 1? Okay, so if I do this, right, I'm going to get the limit, n goes to infinity, of the nth root of n all over the natural log of n. Okay, which I'm going to write limit n goes to infinity, n to the 1 over n, natural log of n. Now, when I look at this, right, if I plug in n, if I plug in infinity, I'm going to get infinity to the 0 all over infinity. So this is indeterminate, which means I need to use L'Hopital's to help me resolve it. Okay, so when I do L'Hopital's rule, I'm going to say the limit as n goes to infinity is the same thing, right? I'm going to take this derivative. So it's going to be 1 over n to the 1 over n minus 1, all over 1 over n, okay? Which means ultimately, like, let's see, let me clean this up. So this is like looking at, let's see, how can I say, how do I want to think about this one? I'm I'm trying to think if I want to confuse you with other ways of thinking about it. I can do, yeah, there are other ways of doing it. I did L'Hopital's on this one here to give me, basically I'm looking at the limit as n goes to infinity. This is n 1 over n times n to the minus 1, which becomes n, there's a limit, 1 over n all over n, right? So I'm kind of getting there, like I'm kind of looping around. It's still indeterminate, right? Which it comes out to be, but this one gets there. I can do L'Hopital's again, but this one comes out to be less than 0 by L'Hopital's. Okay, which means that 0 is less than 1, so therefore this thing converges. Now, there's another way of processing this, okay, which basically means I can exponentiate it. It's like basically saying I'm going to go, let's see, how do I want to think about this one? So I can exponentiate it. And I mean, we can just leave it like this. We can say I can do L'Hopital's again. I'm not going to confuse you with another way of doing it. You can exponentiate it means raise it to the nth power, right? It raise it so that it's like e to the ln of n, e to the n, and then you're just going to take the limit again. But it just, I wouldn't worry about that one right now. Right here, this is fine, okay, for what we're trying to do. Okay, so that one converges. Let's see, 39, number 42. 42, oh yeah. So this one's good. This is like, this actually ends up, this is homework chapter 3.9, number 42. So this one ends up being like, this is a lot like some of the final exam questions that we've seen. So we've got this cone, and in this case, our vertex is at the top. And we've got a radius at the bottom of 8, and I think the height, this thing is, it looks like it's 30. Height equals 30, okay? So again, when we do these, we have to think about coming up with an equation for the radius in terms of our position, in terms of our height position, okay? So, and I think they said, it looks like our water is filled up to 10 feet, okay? So that means our work, we're gonna integrate from 0 to 10, because that's how much water we have. And they told us that the density of the water was 62.4, and I think that was maybe pounds per cubic. Are we in feet? I can't, I'm not seeing units. Yeah, feet. I think that's like pounds per cubic feet. Okay, so that's our density. So we need to take that into account as we're doing this stuff. But let's think about what's happening. So I have my force times the height. Okay, so the height, we can just do this one first. The height is our position, right? Like, where am I at? But like, that's the position of this little sliver of water, like how far. So this sliver of water, right, is 30 minus 10. Now, if I go down just like a nanometer, right, it's like 30 minus whatever that y position is, right? That's the height that sliver needs to travel. And then I'm going to go down. The only time I'm going to go full 30 feet is when my y is equal to 0. So I have to think like how far this little sliver of water is going to go is relative to its height. So the distance that we're traveling is 30 minus y. Travel, or to be lifted, is 30. Our overall height, the height of our cone minus y. Y is that position of that little circular sliver. Okay, so that gives us, that's this height that we need to do. So now the force, I'll call it force. Let's do it force of y, because we want to do it as a function of y. So what I want to think about is, I've got this sliver of circle, right? And it's got this infinitesimally, it's like infinitesimally thick, maybe like we'll call it dy, like that's our thickness. Okay, so I've got this cross-sectional area, which is pi r squared times our thickness. That kind of gives us our volume. And then the force is going to be times our weight density, right, of the water. This is our d, delta is for our density of the water. So, but this part right here, our radius, our radius is going to change, is dependent on the height, right, on our y position. right? Like when we're right at 0, we have a maximum radius, which is 8, right? And when I'm right up here, my maximum height, my radius is equal to 0, right? So I've got to be able to kind of come up with, how do I relate my radius of my circle to my y position? So I'm going to do similar triangles. Right, you can imagine, see, this is a triangle right here. I'm going to take that out. So if I take out that triangle, okay, I'm going to get the bottom is 8 feet. And then the whole distance here, this whole thing is 30, right? So that's part, I'm setting up a proportion where I say the radius is 8 when the height is 30. Okay, but let's say I'm like right about here. I don't know, where that is. So this is my my radius now, my X position, right? So when I'm here, that means that I've gone, how high up did I go? How high up did I went? I went 30. This height here is 30 minus y, right? That's our height. So that means that I'm going to say then this is equal to r over 30 minus y. Okay, so I need to cross multiply and solve for r. So if I solve for r, I'm going to get r equals 8, 30 minus y all over 30, which I can simplify down to 4 over 15, 30 minus y. Okay, so that's, I need to come up with a way of relating my radius to my height. And I'm going to take that right here and I'm going to plug it back into that part right there. So my f of y is equal to pi r squared, 4/15, 30 minus y times dy times our density function. Okay, so all of these things I'm going to plug back into this. So let me scroll down a little bit. So our work, we're integrating, our water goes from 0 to 10 feet. Our force, that's right, so pi 4/15, that's a 15, 30 minus y squared, oops, I forgot my squared over here, squared dy times my density. I'll plug in, this is 62.4. Okay, so let's get all the numbers in one spot and our variables in another. 0 to 10, this is pi, right? So this is 4/15 squared, 62.4, right? And then I've got 30 minus y quantity squared, right? Oops, and I forgot my height. This is our height. Times 30 minus y, and then we've got our dy. So really, what we're doing is we're integrating 0 to 10, pi 4/15 squared, 62.4, 30 minus y cubed dy, and this is our work. And we usually just have you set up the integral. I think the if you want to solve it, it's just trivial to FOIL this, distribute this whole thing out, integrate it with the power rule, and I think I got 721,066.67 pi, or 2,265,297.74. And if you want to do it, but like usually we just say leave it, set up your integral, because the whole thing is just the work, and to integrate it is kind of trivial after that. That was 42. 2018 number 11. Oh, 10 and 11. This is the displacement question. Okay. All right, so this is spring 2018, question 11. All right, so velocity of a particle given in the plane, xy plane, should be xyz plane, v of t is equal to sine of 3t, 5 cosine of t, 3t squared. So it's meters per second. Okay, so find the displacement from t equals 0 to t equals 3 pi over 2 seconds. All right, so displacement means we have to integrate our velocity, dt. And so basically what that's going to look like is we're going to integrate it in place. So I'm going to go from 0 to 3 pi over 2 of sine of 3t. Integrate from 0 to 3 pi over 2, 5 cosine of t. 0 to 3 pi over 2, 3t squared. Because displacement is a vector, so we expect to get a vector out of it. So that means I'm going to get minus 1/3 cosine of 3t from 0 to 3 pi over 2. This is going to be 5 sine of t from 0 to 3 pi over 2. This is going to be 3 times t cubed over 3, so this is t cubed, 0, 3 pi over 2. So now you can't leave it like this. You guys, all this stuff is on the unit circle, so you should be able to come up with numbers. For these things, we expect numbers on this stuff. So this is going to be minus 1/3 cosine of 3 times 3 pi over 2. Well, any multiple of 3 pi over 2 is going to give me a 0 for cosine, right? Then minus a minus, right? Plus 1/3 cosine of 0. So this is just going to be 1/3. So 5 sine of 3 pi over 2, so that 3 pi over 2, sine of 3 pi over 2 is minus 1. So this is just equal to minus 5, because sine of 0 is 0. And then this is 3 pi over 2 cubed. And I can leave it like that. I can multiply this out if I wanted to. So it'd be like 27 pi cubed over 8. It doesn't matter, but this is your displacement. Because displacement is a vector, right? So we're doing everything in place. That's part A. Part B says, find the integral for the total distance traveled. We're not going to expect you to actually evaluate it unless it's easily evaluatable. From t equals 0 to t equals pi over 2. So pi over 2, remember this is different. This is 3 pi over 2, this is pi over 2. So we're going to set up, it says set up but do not evaluate. So the total distance traveled, 0 pi over 2, we're going to do the absolute value. But since it's a magnitude, this means, since it's a vector, this means a magnitude. So that means I go back to the velocity that I was given. I take each term, I square it, and I add those squares up. So I'm going to go sine of 3t squared plus 5 cosine of t squared plus 3t squared squared, sum up square rooted dt, okay? Which is going to give me, I can clean this up, 0 to pi over 2. So this is going to be sine squared of 3t plus 25 cosine squared of t plus 9t to the 4th. And I can't, right, I've got a sine squared of 3t and a cosine squared of 1t, so I can't do anything. But besides, I just said set it up. So now I'm done. Okay. Let me know if you guys have other questions.
Professor, can you please turn the page back to 3.9 question 42? I was just left copying something.
Yeah, you bet. How is that? Is that enough, or do you need me to scroll up a little bit?
Could you scroll up a bit too?
Tell me when to stop.
Bit. Yeah, that looks good. Could you scroll further up to? I think I'm missing something.
Right there's beginning.
Oh yeah, perfect. No, I'm not. Great. Thank you so much.
You want me to scroll down, or are you okay? I'm sorry. Kind of random question, but when I separated telescoping series into two series, both of them diverged while using a limit comparison test of 1 over n. Wouldn't it be the case that if the separate series diverged and the full series diverged, or just that telescoping series is an exception? Telescoping series is an exception, so that's a great question. So let me see. We had well, this one isn't really fair because the if we break this up into two individual telescoping series, they'll converge, right? Because we've got, this is usually comparison with p series. This is a p series. This is a comparison to a p series, but we're subtracting two convergent p series. So it's kind of like, what am I doing? And then I guess if you just had 1 over k minus 1 over k plus 1, say for example, think, is that what you're thinking of? Like one of them is going to be like a p series, the other one will be a comparison to a p series. I think that it's a hard thing because you have to be able, I get what you're saying, because like, why can't you just separate them out, and why does that happen? And that's a really great question. Let me think about that one. And I think part of that is like recognizing what kind of series type we're working with, because the telescoping is a pretty unique series type. Like let's say we had 1 over k minus 1 over k plus 1. Right, so this is like if I were to, and this goes k equals 1 to infinity. So this is going to look like, it comes as a group, right, all together. So let's just do this first, and then we'll think about it as like p series. So this one's going to be 1 over 1 minus 1 over 2, plus the next round when k equals 2. So 1 over 2 minus 1 over 3, plus 1 over 3 minus 1 over 4, plus so on and so forth. So these cancel, I can imagine that one's going to cancel. And the only one that's not going to cancel is our very last one when k is infinity, right? Very last one. So the thing that matters is my first term. So I'm going to go first term, which is equal to 1, minus the limit as k goes to infinity of our next term, 1 over k plus 1, right? So this one happens to go to 0. So we're looking at this thing. This part is our criteria for convergence, and this equals 1 as our sum, right? So yeah, so if I break this up, 1 over k minus 1 over k plus 1. Let's see. So my nth term test isn't going to tell anything, but this is a p series, right, with p equals 1. And then this is, like if I did a limit compare with 1 over k, which is a divergent p series, I'm going to get it also to diverge. So it's kind of like infinity minus infinity, right? Because if it diverges, it's going to diverge. Basically, diverges means it goes to infinity, right? Our sum goes to infinity. So this is like infinity minus infinity, which I guess I can kind of think about that as being like, you know, that's a good question, because I think, you know, usually when we have different series types that we're adding or subtracting together, like with our linearity, then we want to look at, does each individual one converge or diverge? And I think, and I guess the answer, I'm trying to think, this is a great question, but I think the answer is that this is a telescoping series. And so we have to recognize it as a telescoping series, right? I'm trying to think of what other kinds of series we would have that might fool us also. But I think we have to be able to recognize it as such. But it's a great question. What, you know, the highest degree is 1 in the denominator. Yeah, so that's like you're looking at this one, which is a p series, right? So I think the thing is that because it's telescoping, and telescoping is its own special thing where everything cancels out in the end, except for our very first term and our very, like the limit of our very last term, right? So I have to be able to kind of figure out what that's going to be, because it's its own special series. So it's kind of like saying, well, is there a way that I can rewrite a geometric series so that when I sum up these terms, then maybe it looks like a telescoping, because things, you know, alternate back and forth, because r is negative, maybe, for example. So sometimes it'll be positive, sometimes it'll be negative. So I might be able to convince myself it's telescoping. So if I apply telescoping to that, it's not going to be correct. I mean, I guess I'm kind of trying to rationalize it through. And I think that the answer is that the telescoping is its own special series, because it basically collapses. Everything cancels except for the very first term and the very last term. So I don't know if that helps you, but I think you have to kind of recognize it as telescoping, you know. Like I think if I had 1 over k minus 1 over k minus k plus 1 squared, right, that might not be a telescoping series, right? Because then I wouldn't get enough terms to cancel. I'd have bits left over that wouldn't cancel out. And then what I could do is I could separate things out, because they wouldn't collapse. The terms wouldn't collapse each other. Okay. Yeah, that's what I think too. The cancellation property makes it operate, because like I said, if you combined it like this, it's not telescoping, which means I can then separate it out. And so this one will converge, but that one won't, right? And so that then the whole thing will diverge, because this part will be a divergent p series. Whereas here we've got so many things that cancel each other out in the aggregate, except for the very first term and the very last term. So I have to be able to handle it differently. Looks like question exam 2020 number 8. Let me get that one out. Yeah, so where this is a telescoping series. So we'll take a look at that one. So this is exam 2020. If you see a series like what, like this you have to, if it's telescoping, you have to recognize it as telescoping and handle it that way. That's going to be really important, because if you solve it like this, that was the whole question, where if you solve it by separating it and looking at them individually, you get the wrong answer. So you have to recognize it as a telescoping series. And that's why sometimes it can help to do out the first handful of terms. Like this one, this is a great example, question number 8. So this one, n equals 1 to infinity, we're looking at 3 over 3n minus 2 minus 3 over 3n plus 1. This is actually telescoping, although you don't realize it at the time, but watch what happens. So if I enumerate things out, so when n equals 1, right, what do we get? We're going to get 3 all over 3 times 1 minus 2 is 1, minus 3 all over plus 1, so that's 4, plus my next round, it's going to be 3, and when n equals 2, so 6 minus 2, so that's 4, minus This is going to be 3 over 7 plus, now watch what happens. Right, so you wouldn't know it to begin with. You'd think, oh, well, right, it looks like I can just separate this out, but like, I guess a big clue is how you see it like this, right? So it's presented as something minus something else. So before you jump in and distribute and handle it like, I'm just going to take the nth term test, or I'm going to whatever, do a comparison test with the p-series or whatever, do out the first handful of terms, because what you're seeing is this cancels, I'm going to bet this one's our next term, that's going to cancel. So I'm left with my first term. So 3 minus the limit of my next term, 3 over 3 n plus 1. So this becomes 3 over 3, which is, this is just equal to 1. I'm sorry, this goes to 0. What am I saying? Goes to 0. So then this whole thing is equal to 3 minus 0, which is 3, which is our sum. So this thing goes to 0, which means it converges. And our sum is equal to 3. Okay. So yeah, I always, like, whenever I see something like this that's got a couple terms that are being subtracted, I enumerate it out, just like the first handful of terms, just to kind of convince myself, just to see. And if I don't see cancellations, right, then it's not telescoping, and I can do the linearity and then work each piece separately. But if I start seeing cancellations, then I'm going to have to operate it as a telescoping. Now the trick is, right, like this problem here, we've got a telescoping portion and a geometric portion. So you have to be able to, and I kind of tried to give you a hint by this, but let's say it was all being added together. I've got something, they look similar, 1 over k squared minus 1 over k plus 1 squared, and they're being subtracted. So if they look similar, maybe I'll group those and then see if I group those together and I do out the first handful of terms, they should cancel, some should cancel each other. So that means I can process it as a telescoping. So that's part of the deal, is you have to be able to recognize that you're looking at a telescoping, which is helpful if you fill out your table, because then you can write an example of a telescoping series and see, oh yeah, that's what a telescoping series looks like. And then you'll know what the criteria is for convergence and sum, if the sum is appropriate, or if there's a criteria for convergence or criteria for divergence. Okay. Phew. All right, you guys, I think we're about out of time. So I'm going to wrap up here, and then I hope you guys have a great weekend. Is there a download of the table available? Yes, there is. I think it's week 6. It's been on our Canvas page for like a month. When we very first started chapter 5, I put it up there. So it's under lecture examples, and I think it's week 6, but it's under lecture examples, and it says, series table or blank table or something like that. Okay. But you can always, make your own table on a piece of paper, or you can download this one and print it out. Okay, guys, if I don't see you, have a great weekend. Remember, the exam opens tomorrow during class tomorrow, so there's no class. We're not going to meet. Okay. All right, bye, guys. Have a great day. Have a good weekend, too.
Thank
Okay.
you.
Take it easy.
You too. Thank you.
Thank you. Take care.
Thank you.
Bye.